start for today. Today we'll continue with building the continuous time processes. Last time we have started talking about the Poisson process as in a way of counting how many occurrences of something happened until given time. And today we'll see how this works out with the exponential distribution and how this fits within the theory of continuous time Markov processes. Now, you recall from last time we have been talking about the exponential distribution. The exponential distribution is a continuous distribution used for measuring time until something happens. Yeah, we have seen an example on finding out probabilities regarding the arrival of a bus. If we start waiting for a bus, then how long does it take until the bus comes? It can be seen, it has the density in the form lambda e to the power of minus lambda t, where lambda is the parameter of that distribution, and it is called the intensity of the distribution, and it is the flipped value of the expectation. And we have seen that the probability that an exponentially random variable will be larger than some number t, for example, the probability that we will need to wait for a bus for longer than t minutes, can be expressed as e to the power of minus lambda t. That's the survival function or the complement to the distribution function. The density looks like that. If we need to find a probability that variable will be this or less, we just integrate the density from 0 to here. If we need the probability that it will be this or more, we just integrate the density from here up to infinity. Now, we have seen last time that the distribution is actually memoryless. We have seen this when computing the probability that we need to wait for the bus for more than 7 minutes, given that we already waited for 5 minutes, and we see that this distribution forgets, if given the condition that we have already been standing on the platform and no bus came, then this conditional probability is the same as if we just came to the station, as if the process of waiting would be restarted. Yeah, we have seen this proven for that concrete exercise. We can see the proof here. Generally, the probability that we will need to wait for more than t plus s, if we know that we have already waited for more than t, is actually the fraction of the probability of intersection over the probability of condition. We know that probability that we need to wait for more than something is e to the power of minus lambda, the argument, and after working out the exponentials, we get that it is the original probability. This is called a weak memorylessness because it works for t and s which are not random. It can be proven that this also works for in a strong sense, if the time point which we are using as a condition is actually random. Yeah, for example, if we want to find the probability that we will need to wait on the platform for longer than a plus s, where a is the time until the arrival of another bus, which is inherently random. Okay, the probability that we will need to wait for more than a plus s minutes, if we already waited for a minutes, where a is a random arrival of some intermittent bus which we do not care about, which goes into a different direction than we'd like, is if the variables are all exponentially distributed and independent, the same as if we would have just restarted the process. Now, proving this is a bit harder because we need to take into account the distribution of t, the exponential distribution until our bus comes, and the distribution of A, the distribution of the other bus, and put them together. Now, we know that the joint, then if we would like to prove that, we know that the joint density of, well, the arrival of one bus and the other bus is the product of their individual densities, because we assume that they are independent. Now, this is good because we can then find the probability that we will need to wait for more than A plus S minutes as an integral over all options for A. Now, you can imagine that here we start observing. We are observing the time until our bus comes. And here are the options for the other bus. They are orthogonal, they are lateral, they are independent on what we actually want to find out. Now, the options that we need to wait for more than A plus S minutes are given in here actually, because because A can be 0, then we are waiting just for S, but A can be some large constant. Yeah, the first bus can come after 10 minutes, after half an hour, and A plus S still gets us a point here. So the probability that we need to wait for S or more is T being larger than A plus S is given in this triangle. So we integrate the product of the densities over such T's which are larger than A plus S. And here we got A plus S, and what can be A actually? And after rearranging the bounds and working with them for a while, we actually separate the individual densities, break down what we do not need, and we'll get the result that it is the probability that we need to wait for more than more than S minutes times the probability that our bus came after the alien one, which is the condition, and if we divide it by the condition, if we divide the intersection by the condition, we'll get the conditional probability and the statement regarding what we wanted to prove, the strong memorylessness. If we have two exponentially distributed variables which are independent, knowing that one of them already happened, the probability that one of them will be larger than the other plus S, if we know that it is already larger, is the same as the probability that it will be larger than S without actually any input on what was actually the value of A. Now, those are a bit technical corollaries actually, which we need to prove the equivalence of definitions of the Poisson process. But if you like to dwell more on that, you can read through the proofs yourself and see that it actually didn't fall just out of the blind, but that it was actually proven. Now, another thing which we might be interested in is how to express the distribution of a sum of exponentially distributed variables. Now, you can imagine that if we keep standing on the platform at time 0, and we keep the buses running by, and we know that the times between the arrivals are exponentially distributed. Yeah, here is the time until first of them arrives, x1, time until the second of them arrives, time until the third of them arrives, fourth of them, and so on. And now for a distinct number of buses, we might be interested in what's the distribution of the arrival of the fifth bus, for example. Now, it can be shown that this is the time when the fifth bus arrives is just the sum of the individual times, right? Yeah. And it can be shown that if they are independent and exponentially distributed, then they have the so-called gamma distribution. That's a generalization of the exponential distribution for working with sums of exponential variables. Now this is T1, time until the first bus has left. This is T2, time until the third bus has left. And so on, D3, and so on. So, and it can be shown that Tm, time the nth bus has come and gone, follows the gamma distribution with parameters lambda and n, where the density has the form of lambda to the power of n over n minus 1 factorial e to the power of minus t times t to the power of n minus 1 for t is non-negative. And we assume that xi's are exponentially distributed with parameter lambda and independent. Now, this allows us, now this is a function as any other, and it allows us, it can be summoned in any program with sufficient statistical capabilities, and then it can find us the probability that the fifth bus will come in, well, for example, 1 hour, and so on and so on. Now, for the buses, this is not a really practical example because we do not often stand on the platform and let the buses come and go. But we can, and count how long did it take until the 5th, 6,000th bus has actually come. But it makes sense when we are, for example, having a box of some parts, like light bulbs over here, and we want to use them one after another, and we are measuring time, how long does it take until we run out of them, right? If I want light in some distinct room, I insert one bulb, wait until it breaks down, then I insert another bulb, wait until it breaks down, and so on and so on. And if I bought 10 bulbs, I want to know what's the distribution of the time until I run out of them all, right? So this might be practical in certain applications, or when we are running a server and we assume that the times between individual queries which are incoming to the server are exponentially distributed. This is often actually pretty good approximation for the time between the individual queries, and we want to find out how it behaves. Then this gamma distribution actually has its uses. Now, proving that the density looks like this, the density of n of a sum of n distinct exponentially distributed variable goes down to a convolution. Now, you might recall from the basic bachelor's course of the convolution, meaning finding the distributions of sums. Now, if we go way back down and we, for example, roll 2 dice on the table and we want to find out what's the probability that the result is 5, what do? We add up all options on what can happen on one and the other so that they add up to 5. Yeah, so we get like 1, 4, 2, 3, 3, 2, 4, 1. Now the same principle holds for continuous variables, but instead of adding up probabilities, we integrate densities. Yeah, if I have x plus y, which are independent, then the density of their sum is the integral minus infinity to infinity fx times of at the first one times f z minus x of the second one. That's the principle of the convolution, how to find the density of a sum of two random variables. Now, this exactly works in our favor in here because we can use the mathematical induction and prove that if we believe that for n added values x1 up to xn, the density looks like this, and we add one more, it will look like this just with n plus 1. So here it will be n, here it will be n, here it will be n plus 1. And for n being 1, here we have lambda, here we have 1 minus 1 factorial, that's 0, here we have 1 minus 1, that's 0, so it is actually lambda times e to the power of minus lambda t, which is the exponential distribution itself. That's good. And if we assume that this holds for n, and we want to find out using this principle of convolution that if we add n and then one more, so the n plus first variable, and find out what the density is after a while of integrating and playing with the exponentials and polynomials, we actually get that it works out. So this is the gamma distribution. Density actually looks like that, a bit akin to the chi-square distribution. It starts at 0, has a peak in there, and then exponentially decreases in there, and is useful when modeling the sums of exponentially distributed variables. And now we'll get back to the Poisson process, and we would like to prove that it has two alternative distributions. So, Poisson process, definition 1. Okay, so if I would rewrite it in this theorem, if I would rewrite it into the two distributions, into the two definitions, that then can be summarized as follows. Suppose we observe a counting process, counting how many of events has come up until time t, and the times between the events are let the times between events be independent and identically distributed exponentially with the exponential distribution with parameter lambda. And suppose that at n0 the process has the value n0, 0, and nt denotes the number of events up to time t. Okay, so if I take a look at these exponentially distributed times between the events and I put t here, I'm asking how many events actually happened before time t. And I count 1, 2, 3, 4. Okay? That's definition 1. Definition 2 starts again at 0 and let the increments nt minus ns, so the number of increases between time point t and time point s, have the Poisson distribution with parameter lambda times t minus s, and let the increments be independent. Then nt is a Poisson process. With intensity lambda as the result of both definitions. Now, why are they equivalent? Now, you know the Poisson distribution. Yeah, this means that the probability that between points t and s there will be k events is actually lambda to the power of t minus s to the power of k over k factorial e to the power of minus lambda t minus s. Now, why are those definitions actually equivalent? Why is it? Well, in very detail, you will find the answer in the Duret's book or Grimat's book, where it is described until the latest small lemma of the proof. Here we will just take a look at the essentials. Now, those two definitions are coming from really different backgrounds. The first of them just tells us, okay, we are counting how many events happened until time t, if we know that the times between the events are exponentially distributed. Okay, so if I keep the example with the bulbs, for any given t, the counting process tells me how many of them have I already used up to time t. Yeah, it can be 1, it can be 10, and so on and so on. Now, the other definition tells me that at any given time distance between s and t, the number of occurrences has the Poisson distribution, which is discrete. It tells us that the count of variables between points s and t follows this Poisson distribution, and that the increments are independent, meaning that if I keep observing the process for a while, the number of increments which happens in this time period is completely independent on the number of increments which happens in this time period and vice versa. Now, is the idea of the process clear? How it works out? Good. Now, the first thing which comes to mind is, here we are talking about the increments between two time points S and T. Okay. Now, if I put S being 0, then at time point 0 I have, well, measured no increments. And if I put S here as 0, as here as 0, then I know that it has actually the Poisson distribution with parameter lambda times T at time point T. Okay, now these definitions are labeled in a different way than on the slide, so let's just stick with it and first prove that from the second follows the first and we keep them switched. No, sorry. No, they are, I will take a look in the slides first. No, they are okay. That's okay. Yeah, sorry. First is using the exponential times between increments. The second is using the Poisson distribution. Now, if we would go from the second definition, it is pretty simple to prove that the variable ns or nt has the Poisson distribution with parameter lambda times s or lambda times t. Now, we can prove this just by setting this here as 0 and go to this. Now, to prove this from definition 1, from the exponential increments, okay, so let's go from 1 to 2. First, we prove that ns has the Poisson distribution with lambda times s. Now, what does it mean that at time point ns, we have measured exactly n values? Now, this means here I have time s, here I have x1, x2, x3, and so on. This means, so n events up to time s. This is equivalent with the fact that the nth event came before time s, right? And the n plus first came after that. Okay? To have exactly n events at point s, I need to have n before that and the next one after. Okay, so this is xn, this is t1, t2, tn, the time until the n happened, and this is xn plus 1. Okay, so nth event before time s and n plus first event after. Okay? And if we rewrite it down in terms of events, this means that Tn, the time of the nth event, goes before, and at the same time of the n plus first event comes after s. And the nth event actually happens at time Tn plus xn plus 1, so the time before the nth to the n plus first. We know that Tn, the time until the nth event happened, and the time until the time how long it takes from the nth to the n plus first are independent, because that's exponentially distributed. So we can rewrite the probability that this happens into, well, the probability of intersection, and then integrate over all options when what can actually happen. So integrate over all options where the first, well, where the nth event occurs before s, and this one occurs after. Okay, so we take the density of Tn, that's what I already deleted, of the gamma distribution, gamma lambda n, and this xn plus 1 has the exponential distribution with parameter lambda. And we want this gamma distributed variable to be less than s, and this one to be larger than s. So what we can do is take a double integral and just measure the distance between s and t, where this t is the time of the last event. And we know that the time of the nth event needs to be before, and we need the duration what it took from this point to the next to be larger than s minus t. So and that's exponentially distributed. So we take the density of the gamma distribution, then the density of the exponential distribution, and integrate over their respective values, which are allowed to produce this output. And we have seen that the gamma distribution has the density looking like this. The exponential distribution, the density lambda times e to the power of minus lambda t minus s. And if we integrate it from s minus t to infinity, so yeah, because we do not care whether this event happens here or there or there or there, we just need it to happen after point s. So the time, if we measure it from t, to be larger than than s minus t. So we'll get to the survival function t e to the power of minus lambda t minus s. After working it out and integrating, we'll get just an integral of a polynomial t to the power of n minus 1, which is t to the power of n over n integrated from 0 to s, giving us s to the power of n, giving us the actual probability form of the Poisson distribution. Okay, I won't go into into the details how the integrals are reorganized. Those are just representations on how we can rewrite the fact that the nth event happened before and the n plus first happened after the point S. Okay? And this way we know that going from the exponential durations between increments, we obtain that at point S, the process has the Poisson distribution. Now, that's not all what we need. We need to have the increments to also have the Poisson distribution. Not only that at time point S it has the Poisson distribution lambda S, but if we take any difference. Now, and proving that the increments are actually independent. Now, proving this is not that hard. It actually uses the memoryless property of the exponential distribution. Okay. Now, suppose that at point S, we already observed k increments. Now, using the memoryless property, we can show pretty simply that if we know that until time S we already have k events, the distribution until the next time point is exponential, and the probability that we need to wait for more than time t plus the time of the last point plus the difference between S and the last point, given that we know that the next one happened after, is the same as if we just restarted the process. Okay, so if we have tk here, if we have point S here, and if we have tk plus 1 here, then the probability that we need to wait for the k plus first for longer than t, okay, is the same as if we have restarted the process at point S. Now this helps because of the strong memoryless property. Now, this allows us, by then using induction, to prove that the increments of the process are independent, because the time until the next, and time until the next, and time until the next are independent on the times between here, and actually on this whole tk. That's good. And this actually tells us that if we start at point S, already knowing that we have k observations already, it means as if we just restarted the process and we can start counting again. Okay, so if we put t here, then nt minus ns, okay, the number of occurrences, number of events between t and s doesn't depend on the number of events before, which is actually ns minus n0, number of events up to s. Okay, because those are independent variables and the time to the first is independent on the remainder because of the memoryless property. And this means that the probability that this will be equal to, well, for example, k plus, well, this would be equal to some value, is the same as if we have just restarted the process and started at 0, but subtracted the number of observations which we have until then. So it shows us at the end that it actually has the Poisson distribution. Okay, this is not the direct proof of all with all steps, but it goes using the gamma distribution from the independent exponentially distributed times between events to show that the number of occurrences between point t and s have the Poisson distribution, using the fact that the exponential distribution always forgets the property, and using the fact that if we want to find out that at time s we had n probability that at time s we had n events, this means that the nth came before and n plus 1 plus first came after that. Okay? Now, proving the equivalence in the other way around is a bit simpler. Now, suppose that we start at 0 and that the increments have the Poisson distribution. Now, this means if we go, this was what from 1 to 2, this is from 2 to 1. If, well, nt minus n0 is, well, nt minus 0 has the Poisson distribution with parameter lambda times t minus 0, which is lambda times t. Okay. And this means that the probability that nt is, well, k is lambda t to the power of k over k factorial e to the power of minus lambda t. And going from there, what does it mean? Well, the probability that nt is 0, the number of increments up to time t is 0, it is lambda t to the power of 0 over 0 factorial e to the power of minus lambda t. This is 1, this is 1, so this is e to the power of minus lambda t, which is actually the probability that x1 is larger than t. Okay, yeah, that there were 0 increments up to time t. This is 0, this is t. Means that the first increment happened after time t. Okay? Okay, first event happened after time t. And if we take a look at the form e to the power of minus lambda t, that's the survival function of the exponential distribution. Okay, so from this, it necessarily follows that x1 has the exponential distribution with parameter lambda. Okay? Now this goes for the first event. That the time until the first event needs to be exponentially distributed using the fact that the Poisson distribution, the probability that the Poissonally distributed increments until time t be 0 is exactly like this. And if we use the third property, that the increments are actually independent, we can use this for any number of events. Yeah, if we know that the first event happened at time s, here x1 happened at time s, the probability, given this knowledge, the probability that the second event would happen in time larger than t, meaning that there is no event in time s and s plus t, given that there was first event in s, is using the independence of increments the same that there were 0 increments between time s and s plus t, if we know that until time point s we had 1 increment, which is the same as if we didn't know this, because the increments are considered independent, and this again gives us, because we know that this has the Poisson distribution, this again gives us the survival function of the exponential distribution. And this can be done generally for any k being 3, 4, and so on. So from the fact that the number of events up to time t, the number of events between points s and t are following the Poisson distribution, it follows that the times between the events must be exponentially distributed. Okay? Now this would be for the equivalence of the definitions of the Poisson process. I know that this is a bit tedious, but it actually is important to know. Now let's take a look at an exercise 9.1 where we get acquainted with the Poisson process a bit more. Suppose that we are observing our mailbox and we know that messages are arriving to there according to a Poisson process with intensity lambda being 0.2 messages per hour. Okay. intensity lambda being 0.2 messages per hour. And we want to draw a trajectory of our incoming messages now. Let's take a look. The process MT counts us the number of messages which arrived up to time t. Okay, so we start at point 0. And start observing. Now at this point, a message arrived. So there is one in our mailbox. Then for a random time, there is one message still, then another is incoming. So the process jumps to 2. Then we wait until the other, then it jumps to 3, and so on, and so on. Okay, so this is the trajectory of the process. It jumps up by 1 at the observed times of the arrivals of the messages. Okay. Now, part B is pretty simple. Asks us what's the expected time between arriving messages.
Is the lambda value, right? Wait, no.
Not exactly.
Yeah. Hours times.
This is messages per hour. And we want to find the expected time. So it cannot be directly lambda.
Lambda times something.
Lambda times t and
Not really. Now, from what we have been just talking about, what's the time between two messages? Let's say here, that's x1. Let's say here, that's x2. Those are times between messages.
Also, it must be 5 hours for one message.
Why is that?
Because 0.2. And we want to get like one full message, right?
Yeah.
Not a partial one.
So we want to get lambda up to 1, so we multiply it by 5.
Not directly. No. Now the times between messages are exponentially distributed with parameter lambda. Okay. And what is the expectation of the exponential distribution? We have computed it last time.
NP.
Sorry?
NP.
Oh, the integral.
Yes, that's the integral. We have computed it using per partes, but what was the result depending on lambda?
1 over lambda.
1 over lambda, right? This is a good thing to remember. If the intensity is 0.2 messages per hour, this means 2 messages per 10 hours, meaning 1 message per 5 hours. Then the expected time is 5 hours, right? Okay, so 1 over 0.2, which is like 1 over 2 over 10, 10 over 2, which is 5 hours. Yeah, it is like hours per message, okay? Does it make sense?
Yes.
Good. So, courtesy asks us, what is the probability that we will find exactly 1 new message after an hour? Probability 1 message after an hour. That's the probability that n1 after an hour will be equal to 1.
1 by 5.
0.2, just lambda.
Not exactly. Now we know from here that the number of messages until time point t has the Poisson distribution with the parameter lambda t. Yeah, if we put 0 here, 0 there. Okay.
Lambda to the power of k over k factorial.
Lambda times 1 to the power of 1 over 1 factorial e to the power of minus lambda times 1. Yeah, we know that generally probability that nt is equal to k is lambda t per k over k factorial e to the power of minus lambda t. So 1 message, k being 1, after an hour, so t being 1, is exactly this. So this is lambda, so 0.2 times e to the power of minus 0.2 times 1, bringing us to, if I put it in, oops, where do I have it? In here, yeah. 0.164. Does it make sense?
Yes.
Here we see how the exponential distribution for the inter-arrival times, the times between messages, is connected with the Poisson distributions, the number of messages in some time period. Yeah. The next part, probability that there will be no messages after an hour, is the same, but with probability of n1 being 0, which is lambda times 1 to the power of 0, 0 factorial e to the power of minus lambda times 1, so it is e to the power of minus 0.2, which is 0.819. The next part is pretty simple.
Professor,
Yes.
if why are we not thinking it like the way that we are getting one message per 5 hours? As per the second question, we are getting one message per 5 hours.
This is like this.
And we need to get one message after an hour. So for the first, if we are starting our time from first 4 hours, so it will and if we are starting in the 5th hour, so at that time only we will get the message. So
Now, careful. This is an average behavior. Okay. The expected time between messages is, well, 5 hours. But it doesn't mean that the messages will be arriving exactly after 5 hours. Yeah, it can happen that they can arrive shortly after one another, or there can be a really long delay. That's possible. Because we will observe just one realization of such a process. The times of arrivals are random, yeah, and the expected time is just an average behavior, okay? And the fact that we are dealing with the exponential distribution actually means that we can restart it at any point. And if we have already waited until here and received no message, and we would use this as a condition, it would be the same as if we just move the x here, okay? So this is a bit counterintuitive, and the thing here we must only take as the average ideal behavior, okay?
Yes.
Now part D asks us, what's the probability that we have received no new messages in 24 hours? That's pretty similar. No messages in 24 hours. This is the same as the probability that the process at point 24 is 0, which is, well, the same as before, lambda times 24 power 0 over 0 factorial e to the power of minus lambda times 24, so e to the power of minus 0.2 times 24. Yeah, that's e to the power of minus 4.8, actually being 0.008 about. This is just inserting into the same formula of the Poisson distribution. The interesting thing is part E.
Sorry, one question. In this case, in letter D, it doesn't matter that we haven't checked, right? Because the events are independent. So whether we check or not check, that doesn't change the probability.
Yes, yes.
Okay.
We are just setting up the situation. Suppose that you have come to your mailbox and you are finding what's the probability that it will be clean.
Okay.
Okay, now part E asks us, if we take this as known, what's the probability that we will get at least one message in the next 30 minutes if we have received no messages in the last 24 hours. Probability message. One message. Okay. The assignment asks us for at least one message in next 30 minutes. If we know that there was no messages in last 24 hours. at least one. Now, how can we rewrite this?
The probability that one message will come in 30 minutes in 0.5, or k equals 0.5.
Probability that
That t equals 0.5. Well, and that's
Intersection of.
and that's 1.5. Does it affect that we haven't received messages?
Okay, now let's break down what we know. Here we started observing there were no messages until hour 24, and we are looking at this time period.
Could you say it as 25, like between? Because in N25 that means that we received something. At least one.
You know, 1/2 an hour, so and 24.5.
Okay.
Now, and what's the number of messages arriving between this and this? This can be written as n 24.5 minus n 24. Like number of new messages arriving in
Greater
this
than
time period being greater than equal to 1 if we know that n 24 is 0.
So it's like survival function, but
Uh-huh.
equal.
It is memory less, right? So we don't care that we're having 0 messages yet.
Now this is pretty important. This is like n24 minus n0 being 0. And those are non-overlapping time periods. And from what we have seen about the Poisson process, it has independent increments. What happens, this is an increment, right? The increase of messages in our mailbox in some time period is independent on what was the increase in this time period. Okay. The important thing is that those two time periods are non-overlapping. Okay. So this is the same as if we didn't know anything about this. So there's the probability n 24.5 minus n 24 being larger than equal to 1. Okay. And how can we find this?
Complement?
Pretty simply. 1 minus probability that n 24.5 minus n 24 is strictly less than 1. And now, because they are integer valued, this means that it is 0. And now we know that this is a difference, so it has the Poisson distribution with parameter lambda times the difference, so 24.5 minus 24, which is just 0.5. So this is 1 minus, and now lambda times 0.5 to the power of 0 times 0 factorial e to the power of minus lambda times 0.5. So this is 1 minus e to the power of minus 0.2 times 0.5, which is 0.1. Yeah, 0. Which gives us at the end 1 minus 0.00905, giving us 0.9095. That's not that important to know the exact probabilities. The important thing to know is that the Poisson process has independent increments. It actually gets restarted at any point which we start observing it. So the number of jumps of the process at any time period is independent on how many jumps have been there in the past. Okay? And the probability that in a given time period we will have exactly some number of jumps is governed by the Poisson distribution. Okay? Now the interesting thing regarding the Poisson process and the thing that it forgets its history is that it can lead us to establishing the actual continuous time Markov chains. Now, so far, does it make sense? Okay. Now, let's observe the process at generally any time points from 0 going through time point t0, t1, t2 up to tn minus 2 and then time points t and t plus s. And going through the probabilities that if we know what were the values of the process, how many counts did we have until time t0, t1, t2, tn minus 2, and time t, does not change the probability of the increments between point t and point t plus s. Okay, the probability that at point t plus s we will have exactly j messages, if we know that at point t we had I messages given the broader history, is the same as the probability that between point t and t plus s the process has increased by j minus I. Okay. And given the further history, and because of the independence of increments, it is the same as we didn't know about the history. Okay. So, observation. Using the independence of increments, the probability that at time point n t plus s, between time points n t plus s and n t, we have made an increase of j minus I, given the broader history, is the same as if we didn't know the history. And it has the Poisson distribution of lambda times the difference t plus s minus t, which is s. So this is actually lambda times s to the power of j minus I over j minus I factorial e to the power of minus lambda times s. Okay. This means that we have j minus I new jumps between time points t and s. And for so we have I events up to time t and j events up to time t plus s is equivalent with having j minus I events between times t and t plus s. Well, it's not exactly equivalent, but the probability is the same, and it is the same as having j minus I events between 0 and s, because of the Poisson distribution being independent on the shift. And for j minus I being 0, we can just insert and get that it is the exponential. For 1, we'll get that it is the exponential times lambda s, and so on and so on. And we would be interested in how this behaves in a really short term, if we take a look only a small short-term step forward. Okay, so instead of s, let's take some h, because h is often associated with being small.
Professor, what is that? J minus I events between
0 and s.
J minus I events between times t and t plus s, and this is j minus I events between times 0 and s. Okay? For h small, we get that probability that n h is equal to, let's say, j minus I 0 is, well, lambda times s to the power of 0 over 0 factorial, so e to the power of minus lambda h, and probability that it is exactly 0, we'll get that it is lambda h times e to the power of minus lambda h, and probability that it will be 2 or larger is then lambda h to the power of 2 over 2 factorial and so on. And it can be shown that when comparing it to the length of the small time period h, it can be written down using the Landau notation. You might have seen this on the calculus, OH, where the OH is something small when compared to h. And the exponential, actually, if you do the Taylor expansion of the exponential, you'll get that this is 1 minus lambda h plus something small This is lambda h plus something small, and this is something small. This will then lead us to be able to work with the process as if it were continuous time Markov chain, which it actually is. We will see that in a short while. Now, let's take a look. You recall from last week and the one before that we have talked about discrete time random processes which were homogeneous Markov chains. We assumed that they had the Markov property telling us that the probability that they jump between two states, given a broader history, is the same as if we didn't know it. And we declare this property for continuous time processes in the same way, but not looking one step forward, but any amount of time forward. So, okay, so definition, a continuous time process xt is called continuous if from a continuous time Markov chain if for all states, let's say I0, I1 up to I k minus 1, I and j out of the set of states, and for all times t0, t1 up to tk up to s up to s plus t, it holds that the probability that the process will be at state j if at point s plus t, if we know that it was in state I at time s, given the broader history, x t k minus 1 being I k minus 1 up to x t0 being I0, is the same as if we didn't know the history. X plus t being j, if we know that s is I. This is called the continuous time Markov condition. The probability of jumping from state I to state j between time points s and s plus t is the same regardless of where the process has been before. For any time point s and for any future time point t. Okay. For the discrete time processes, here we had n, and here we had n plus 1. Okay, we were just going one way into the future. We are just looking on the probabilities of transitioning one step into the future. Now, in this context, we are looking any time period into the future. Now, in the same way as before, we can define the distribution at time t of the process as a vector of probabilities and the matrix of transition probabilities in between time points s and t as the probabilities of jumps between states I and j when observing the process at points s and t. T or s plus t. Yes, here we have this. Now, further, we can then say that a process is a continuous time Markov chain if the probabilities of going through a number of states can be written using an initial distribution times transition probabilities between individual states and in individual time points. And it can then be shown that for the matrices, the Chapman-Kolmogorov equations hold the same way as for the discrete time processes, but at this time for any combination of time points s, t, and r in between them, that's just probability of transitioning between states between time points s and t are matrix products if we choose any time point r in between. Now we call definition the continuous time Markov chain homogeneous if for all s and t it holds that the probabilities of jumping from state j to state I between time points s and t are the same as if we had just started the process. And in terms of matrices of jumps, matrices of transition probabilities, it means that the matrix of transition probabilities between time points s and s plus t is the same as transition between time points 0 and t, and we can just take it as the matrix of transition probabilities representing the process, the behavior of the process. So the matrix of transition probabilities of a continuous time homogeneous Markov process is defined as P at point T, which is a matrix which again has the probabilities of going from state I to state J in amount of time T. Okay? We can imagine that those would be probabilities for the Poisson process. Those would be probabilities that if I started with some amount of messages already in my counter, was the probability that after T hours I will be having J messages. Okay? And when compared to the discrete time random processes, the matrix of transition probabilities in that setting was just a matrix of constants. Yeah, there were probabilities inside, and we were able, if we were in some state, we were able to say immediately that in the next step, we will be in this state with a given probability, in that state with a given probability, and so on and so on. Because the time was discrete, measured in equidistant time frames. Here, the time is continuous, and this matrix gives us the probabilities for any amount of time which can pass. So those are actually functions of time. Yeah, if I am in some concrete state I, what's the probability that I will move to this, or that state after 1 hour, 2 hours, 5 minutes, and so on? Okay? So this is, and you can imagine that this is not that practical to work with, because those are not constants in it, but functions. We will see after the break how can we simplify dealings with continuous time Markov chains and how it all ties with the Poisson process. Okay? Does it make sense so far?
Yes.
Good. Okay, so we'll make a 15 minutes break and we'll move on.